So, hello back. This is the lecture on linear regression. So, with the perceptron, we started to define this h of x function and then applied a threshold function. The linear model is even simpler. We leave the threshold function away. So, the output is the h. So the output is a linear weighted sum of the inputs. Otherwise, on the left side, you see it looks exactly the same. So after we have the model, we define a cost function. And the typical cost function in regression is the squared loss cost function. So it's a sum over all data points. And then you take the difference between the prediction of your model, fw of xi, so this linear model, take the difference with respect to the true target of this training data point, and you take the difference and square it. So the square of the difference is non-negative, and it's minimized if you obtain the best fit. The parameter which minimizes cost function are called least squares estimator. So W least squares is the argument with the minimum cost. So the weights with the minimum cost according to this least squares cost function or squared loss cost function. So for visualization, we take m equals 1, so there's only one input. Of course, linear models are typically applied to high-dimensional problems. So here, our model is W0 plus W1x. So we have two parameters, one for the offset, one for the actual input. The cost is simply the difference between prediction and actual data point to the power of 2. And here you see that the data points are typically noisy. So you cannot go through all the data points unless the dimensions are really high. So you see here a fit, and maybe this is close to the true function, but there's no expectation that we fit all the data points. So there is a residual error. Here we cannot fit, or we don't want to fit because it might be simply noise on the data. So the general model is the prediction is W0 plus sum from 1 to m over wj xij. And we can write this conveniently as this product, the x transpose w, or xi transpose w, and w is the vector which contains all the weights, and xi is the inputs to the ith data point, xi1 to xim, plus the constant input offset, which we always have also here. This is how it might look like in 2 dimensions. So the regression becomes a manifold or a 2-dimensional beast here. So here we have y, the output, x1 and x2. Here's the fit. But you see that the data points might be a bit away from this regression function. The really nice thing is this squared loss function, because if you consider one data point and you plot the contribution of this data point to the cost, if you vary hi, then if you have a perfect match, there's zero contribution, and then if you go away from this match, the cost increases quadratically. So this is really, I mean, that's sort of the best cost function for numerical issues and for optimization. So we can write the prediction problem for all of the training data points in this convenient form. So if we have model parameters W, we multiply it by this design matrix X, which we introduced in the last lecture on the perceptron. And we can also write the prediction vector for all inputs in the training data set as a vector, and then we have this nice formulation y hat equals design matrix X times W. And as before, we can do gradient descent learning. So we initialize parameters, typically using small random numbers. Again, we adapt the parameters in the direction of the negative gradient. And so the cost is the sum over the square difference between prediction and actual target. The parameter gradient for weight W, so the derivative here, equals 2 times this expression. So 2 times this expression, then times the inner derivative. So if you have this wx, we take the derivative with respect to w disappears and the x is left over. And since there was a minus sign here, the minus sign goes in front. And this is the gradient of the cost with respect to wi. And so we want to go in the negative direction of the gradient, so we can adapt wj is the old wj plus eta, sum over data points, target minus prediction times xij. So if we adapt j, the j appears here, it's sum over all data points. And of course, there's a stochastic gradient descent version of this. So this whole concept was invented in machine learning around 1960, and it's called ADALINE. Stands for adaptive linear element. The term is not used too much anymore, and the learning rate for the ADALINE is the new W is the old W plus eta, so the sum drops out because we are doing pattern-based learning or stochastic gradient descent. The difference between the actual target and the prediction times x tj, and we do this for all w's. Again, eta is a learning rate, typically small number, and formally it looks like it's the same as the one version of the perceptron learning rule, the one I introduced in the appendix. But of course, here we are, the y hat is the weighted sum of the inputs in the perceptron. It was after we applied the threshold function. So the ADALINE is typically optimized by stochastic gradient descent. And this can be also quite beneficial. For example, if the system changes in time, but the system continuously produces data, then the ADALINE learning rule can track the changes. So it's also a form of adaptive online learning. And it's, in fact, in this domain, it's still one of the most important algorithms. But with a fixed data set, the least square solution can also be calculated analytically, and this is what we want to do now. So to do that, we first consider our cost function again. And we notice that it can be written in this form. So y minus big X times W. So this is a vector, and we take the transpose of this vector. This is the same vector, so this will give a number or a scalar. And as I said before, Y is the column vector of all Y targets, and big X is the design matrix. And if you write this down, it's a sum over, it's exactly this term, this function over here, because it's sum over the squares of these expressions. So you should maybe try to derive this yourself. If you remember from school or from studying, the necessary condition for an optimum is that all the first derivatives are 0. And since we have this nice quadratic cost function, it turns out there's only one optimum. It might be degenerate, but if you have enough data, it's a unique solution. So I want to motivate a little bit the matrix equation which solves this problem. So let's first consider we have only one input and no offset. Then it's just the target minus X times W squared. If we take the derivative, it's the inner derivative times the outer derivative. So here we get the square with respect to the W, and here 2 times target minus XW. This becomes the expression we derived before, minus 2, the sum of all data points, xi1, is only one input, y1, xi1, w1. And now we can take these products here, so this product and this product, and we get the minus 2 sum of all data points, x times y, and then plus 2 times w, the sum of all data points, xi1, xi1. And so we want to set this to 0 because all derivatives have to be 0. And then we can bring the w, first of all, put this equation, this part of the equation on the right, on the left side or the other side of the equation, and then we have to divide it by this expression, which is really a number. So we can write it in this form. It's the sum of all data points of, so it's only one input, so it's input squared. The inverse of that, because then we have to divide by this, times the sum of all data points xi1, y1. And we can even use this nice vector formulation. So this, as I said before, is y minus x1, w1, y minus x1, w1, where this y bar is x11 to xn1. And so this is a vector. And I can take the derivative as before, and I get this equation, and then if I sum over them, so the sums now become inner product as before. And we always had this played this trick. So now we have an inner product of the inputs transpose times y times the targets plus 2 times w times the inner product of this vector with itself. So it's exactly the same formula as this formula, just written in a form which is an inner product, so the sum disappears. And if we now solve for w1, the least square solution, exactly the one before, it's x transposed x, inverse of that, times x transposed y. So this is just another way of writing this, if you got confused. But this looks like a formula we will have also in a moment in the more complex setting. I just want to give you a feeling a little bit why this equation looks like this. Because now we're doing the multi-dimensional input. So the function is x transpose w. X now has many dimensions. Cost function is y minus x w transposed. times y minus xw, as we discussed before. And now we have to apply also again the inner derivative times outer derivative rule. So before it was this expression, now it's y minus x transpose w, derivative with respect to w, 2 times this expression becomes this expression now, 2 times y minus xw. And this then becomes minus 2 x transpose times y minus xw. And we can take these terms together again, minus 2 x transpose w plus 2w x transpose x. And then the generalization of this formula is this famous least squares solution. So this is really an important solution. So here we take the design matrix transposed times the design matrix. So this will have the dimension of parameters squared, so m sub p squared. We take the inverse of that, we multiply it by x transposed and by the vector of the targets. Yeah, so how do you take the inverse? You just plug it into an appropriate program like MATLAB or something similar, which does this calculation of the inverse for you. Yeah, it's sort of scary to think about that these type of equations were done manually before the computers appeared. I have no idea how they did it, but nowadays we have convenient computer programs which help you, like Python or MATLAB or similar things. And hopefully by motivating it by these two steps, this equation doesn't look as strange anymore, or you sort of can understand a little bit what's going on here. So here's the least squares equation again. How expensive is this? So m is the number of inputs. Probably it should be a number of parameters. So number of parameters to the power of 3, so cubic in the number of parameters, and then there's another expensive term which is n, the number of data points, times m squared. So it's sort of cubic in the number of data points, in the number of parameters. That's sort of, although this term is often more expensive, but so the inverse of a matrix scales to the third power of the dimensions. So here we get these parameters out for this data set, 0.75 for the offset, and W1 is 2.13, so it's a slope in this case. So this is an important equation. Maybe you can try to get familiar with a little bit what this means. Technically, you can just plug it in any MATLAB or whatever software environment you're having. And the nice thing is we don't have to do this iterative least square stuff anymore. We can get the solution in one nice algebraic formula, and it's deterministic. So if you plug this into a software, you always get the same result. So we don't have to deal with this learning rate and decreasing the learning rate and all these sort of things. Oh yeah, if you look at these equations, essentially I hid it a little bit from you. We took derivatives of different products of matrices and vectors. Here's just a collection of formulas. So the derivative of A times X is A transposed, so with respect to X. Of X transposed, X is 2X. Of X transposed AX is A plus A transposed X. It depends a little bit if you define it as a matrix or the transpose of the matrix. So sometimes you also find these expressions in the literature. I think we use the first one here, but you get, of course, the same results. These are not necessarily formulas you have to remember, and I think we will never use this stuff before, maybe one or two occasions. But otherwise you probably don't understand what's going on here unless you say, oh, it's similar to here. Yeah. Okay, so if the number of data points is much larger than the number of parameters, then everything is stable and the parameters are typically well defined. And small changes in the data leads to small changes in the estimates. When the number of data points is smaller than the number of parameters, then there are many solutions which would all produce zero training error because you have so many parameters to fit the data. So in this case, if we have more solutions, because problem becomes to generate, we have fewer data points and parameters. One selects the one where the sum over the weight squared, which can also conveniently be written as W transpose W, is minimum. So why not? No? So this is if there are many solutions and this one is also has zero training error, why not pick this one? But it turns out even if the number of training data is larger than M, or if they are both approximately of the same size, it is a good it's a good idea to add this term to your cost function. And this is called regularization. And what we're doing now is called penalized least squares, or PLS. In statistics, it's called ridge regression. Machine learning is sometimes called weight decay. And the idea is also that the influence of a single data point should be small. So what we are doing is we're changing the cost function. We are minimizing the square difference, the square of the difference between the prediction and the target, as before. But now we also say we want to have a small sum of weight to the power of 2. And here's some parameter we have to choose, some lambda, some number larger than 0, positive number. And later we'll discuss how we get this lambda. And if we add this term, our solution just changes slightly. Before we had x transpose x to the inverse, x transpose y. And now here in this term, we just add this lambda I. So the penalized solution is slightly different from the least square solution. And it turns out this addition of this lambda I always makes the solution stable and unique. And you can make the same calculations before. You calculate the derivative of the cost function with respect to W, get the terms from before, and then from this term you get the two lambda W, and if you then solve it for W, you get this equation. And this is also very important, and it's a little bit like a magic bullet. Adding regularization almost always improves the solution. We can also look how it looks like in stochastic gradient descent. So here we have to divide the contribution by the number of n. So instead of lambda, we have lambda of n, because otherwise you would put too much weight on the regularizer, on the penalty term. Now I have a toy example to demonstrate some of the nice facts about regression models, and probably generalizes to many multi-dimensional models. So we only have I don't know why the title seems wrong. Okay, so we generated n data points with 3 inputs, so no bias to make life a little bit simpler. X1 and X2 are highly correlated, so they are almost always the same, and X3 is independent from X1 and X2 and also Y. So x3 really has nothing to do with the whole problem. Then we generate output data with the model or the function y equals x1 plus epsilon, where epsilon stands for independent noise, with a standard deviation of 0.2 and thus variance of 0.04. Thus the ground truth parameters are 1, 0, 0, and y only depends on x1. So the true function is y equals x1, drops out, plus epsilon. Okay, so what happens? So the first thing is we build models where each model only uses one of the inputs. And it turns out the coefficients are the same as the one you would get out, what is called the Pearson correlation coefficient, written up here. And then we have three models, and the models are, so with the first input, y hat is 0.99 times x1. And that's quite nice because it's exactly the underlying true relationship. Unfortunately for x2, we got almost the same dependence. Y hat equals 0.96 times x2. Of course, the reason is that I generated x2 to be highly correlated with x1. And so this, of course, is not there in the real world. Y depends on x1 and x2, not on x2. But if you only model the dependency on x2, it will not know that there's another x1. So it does it best to fit the model and gives a pretty large parameter. And for the third one, you get this small negative parameter weight. We can do a little bit deeper analysis. If you want, it's in the appendix, but you don't need to understand. So the mean of this is correct, is 1, and the standard deviation is 0.02. So this reflects the true dependency. Second coefficient that would also have a mean of 1 and the standard deviation of 0.02. So that's the same as here. And the third one has also a mean of 0. So the mean would be the real one because everything is uncorrelated, and a standard deviation of approximately 0.1. So, and this is also something you notice a lot in machine learning. Even if I have the wrong model, I condition on 2, the prediction might be completely high quality, so this gives you a very good prediction. But the causality is wrong. There's no connection, no causal connection. This is the right causal model. But if x1 is missing, if I don't know about x1, I see a nice dependency, and if I'm not very careful, I interpret it as a causal dependency, and this gives you all these problems with causality analysis. Yeah, we can look at these matrices. So x transpose x looks like this, and here you see the big numbers, which so one can show that this is approximately n times the covariance. Covariance is sort of 1 here, so everything is close to 1 if you divide by 100. This is the inverse, and if you in the third term, the x transpose y gives you these numbers. And if you calculate the least squares solution, you get these parameters. So the model becomes, and now we are doing a multivariate model now. So we have all the inputs. Y hat is 1.137 times x1. So this should be 1, maybe close. Minus 0.15 times x2. So this should be 0. At least it's closer to 0. Minus 0.018 times x3. So the linear regression pretty much identifies this strong dependency on x1. And deeper analysis shows that on average this is in fact 1, and the error on this one is 0.1. So the estimator is what's called unbiased, but the uncertainty is larger than in the unit dimension analysis. The analysis also shows that this one is really, and the mean is 0 and the standard deviation of 0.1. Thus the bias is removed if compared to Pearson, because in Pearson this would be a mean of 1. If we add these two contributions, because these guys are almost the same, we see that the prediction is excellent because they add to 0.98, which is really close to 1. And so here we see a little bit the magic of multidimensional analysis, which shows you that the true dependencies is discovered with higher likelihood. And so the third weight is also much smaller, much closer to 1. So in regression, the causal influence of X1 stands out much more clearly, and the influence of the correlated input X2 and the noise is largely reduced. So there's an important application in healthcare. So consider X2 is a medication, and Y is the outcome of the treatment. If I do a unidimensional analysis, so only model X2 is the input, Y is the output, I would see a strong positive influence of X2 on Y. No, this influence here. But of course we know that there's no dependencies because the dependency is really from X1. And this is what in medical in healthcare is called a confounder. So there's a variable we don't know about. No, we only know about X2. But it's correlated with the other input, so it's even the cause of the other input, and it's also the cause of Y. No? So that's why it's so important to do a careful analysis and try to find all the important inputs in your modeling in healthcare if you want to draw valid causal conclusions about, for example, the effectiveness of a drug. So here's a plot, number of training data, and here are the 3 weights, and they so with and larger, the weights become more accurate. So this converges slowly to 1, this to 0, and this eventually also to 0. And if we look at the test error, then with very small values, we have instability because we don't do regularization. And then we have more or less a nice learning curve. The test set error goes down. So this is not a training error, it's a test set error. So which we're really interested in machine learning. One way to explain this is if you write this model in this way, y minus y1 x1 minus y2 x2, then this term only has to explain the difference between the target and what's already modeled, whereas in the univariate analysis this term had to model the whole thing without these terms. So since everybody only has to focus on the difference between the target and what the other inputs are doing, you get truer parameters and also less variance in your estimates. So here it's shown again. So x1 causally influences x2, causally influences y, and there's a strong correlation to x2. So this is also the cause of x2, and x3 has nothing to do with it. If we do univariate analysis, you see this strong correlation here, but you also see shine correlation here. There's not really a dependency, and we get this parameter here. If we do a multivariate analysis with penalized least squares, which I discuss in a second, this one becomes even close to 1, this becomes very close to 0, this becomes also very close to 0. So here we see the true dependencies. Now we do we add this regularization parameter, 0.6, so well selected. So this matrix changes a little bit. We have more power here on the diagonal. This changes a little bit. And if we calculate the penalized solution, we see that the true parameters are even, the fits are even closer to the true parameters. So here you see the benefits of adding a penalty term. And the equation would be this: y hat equals 0.99 times x1 minus 0.1005 times x2 minus 0.021 times x3. Here is lambda, so this regularization parameter, and we increase it slowly. And you see that initially, that's why I picked it here. So let's first look at the test set error. We see with small lambda, we get a certain error. If we increase lambda, the error goes down. And if we make lambda too large, then the error increases again. So it's sort of important to be in the right area here with your lambda. You don't have to be perfect, but you should be close. And it happens that around this value, 0.6, in fact, this weight is 0, W2 is also close to 0, and W1 is close to 1. Here you see the behavior as a function of n, the number of training data, with lambda equals 0.6. So you see, compared to the unregularized solution, that these W1, W2 more quickly converge to the true parameters with n. You should compare it to this plot, where even with 100 data points, the green one was not so close to 1, and now it's much closer to 1. And also the test error behaves more nicely and more stable. So Pearson thought the Pearson correlation coefficient, named after him, was really something scientific and independent of any causation or causal influences, causal assumptions, and can be objectively measured, which is sort of true, but the interpretation is difficult if you want to have a causal interpretation, and that's what you typically want to have if you want to check if a medication works on observed data. You are interested in the causal effect of the medication and not in the correlation. So the regression coefficients display causal behavior much more closely, but causality analysis requires a complete models. If you leave important inputs away, if you're not lucky, then you will see these apparent correlations. So if you're only interested in prediction accuracy, so not in the interpretation of the model, you can add more inputs than you might need, because if you apply regularization, it sort of takes care of the inputs which are irrelevant. Of course, you can always do too much, but you don't have to be extremely careful. For example, in advertising placement and advertising bidding, hundreds of thousands of features are used. With regularization, useless inputs, the weights on them become close to 0. Regularization is especially important when the number of training data is sort of the number of parameters, or when even you have fewer training data points than parameters. But of course, if you want to interpret your model, and also for computational reasons, maybe you want to keep the number of inputs small. And there are two basic strategies. One is forward selection. You start with a model without any inputs, an empty model. and each step you add the input that reduces the error most. And backward selection, pruning, you start with a full model, and at each step you remove the input that increases the error the least. So these are sort of so-called greedy strategies, and you can be more smart about this, and you can give probably a whole lecture about how you do this. But it's, yeah, if you're really interested in this, you can look up in the textbooks. But there's no guarantee, because it's NP-hard, that one finds the best subset of inputs or that one finds the true inputs. So you have to be a little bit careful, or the expectations should be too high. So here's some real experiments, 8 inputs, so it's cancer data, prostate cancer data, 97 data points, patients, Y is a prostata-specific antigen, and you test on the, evaluate on the test data, on some data you didn't use for training. So least squares without anything fancy gave you this error, 0.586. If you do best subset selection, you ended up with 3 inputs from the 8s. It gives you a little bit better performance, but rich regression gave you even better improvement. So which also shows that regression is really good for getting good predictive performance. But if you are really interested in interpretability and want to remove inputs which might be highly correlated with other inputs, you might want to do the subset selection procedure. So ranking in search engines, for example, the relevance of a web page to a query, one uses high-dimensional linear systems, or advertisement placement, where to put which ad for a user. And here people design inputs very smartly by doing what is called feature design, we'll talk about later. So here I put in the appendix the analysis. It's more for me than for you. It's probably not really understandable, but you're welcome to look at it. So it's the analysis of the expected mean and the variance, and I was happy that I could do it with pretty limited complexity, but it's not really so important for you. So yeah, to wrap up, so linear regression is extremely important. It's used, for example, in statistics a lot, because for small inputs, even dependencies which might exhibit some nonlinearity at some point, for small inputs, a linear model often gives you good results. The solutions for least square and for penalized least squares can be calculated in closed form, so you don't have to go through this eta iteration or stochastic gradient descent. You can just calculate the solution in closed form. And also similar what I told you about the perceptron, it really works well if you have a lot of inputs, and in the next lecture on basis function, you might get a better feel for why this is the case. Okay, thank you very much for listening.